guys, so I think where we left it off last Friday is I did a really bad job of explaining how flip-flops worked and confused the heck out of everybody. So I decided to take a step back because it is a real confusing thing. So I made a simulation. I was going to show you guys the spice simulation for a flip-flop. It's easier to kind of poke at the different nodes inside the flip-flop so you guys get an idea. But the first thing I wanted to do was to take a step back and talk about a couple of things in the latches and the flip-flop that are sort of unusual before we get going. So you guys just got done with a CMOS inverter example, right? So we have that an inverter is a P and an N with the inputs connected. So the P supply is connected to the highest supply, the N supplies or the source is connected to ground. The inputs are connected together and the outputs are where they meet. So that's the simplest CMOS gate. But a special, like the general rule for CMOS gates is you would have a pull-up P network. What happened? Why is this thing not responding? I don't know why it's not responding. Hello? Sorry, guys. What? What am I doing wrong here? I can't scroll around all of a sudden. Let me try closing this thing. So just as a general CMOS combination logic. So you have a what am I doing? You have a pull-up P network and a pull-down N network. And the P network is hooked up to VDD. The N network is hooked up to ground. Where they connect together is the output. And the inputs go to both sides. And so that's a general case. In the case of an inverter, the pull-up network is just a single transistor and the pull-down network is a single transistor. If you had like a NOR gate, you'd have the pull-up network would be two PMOS transistors and the pull-down network would be two NMOS transistors. But this general case would hold. The middle would go to the output, the inputs would go to both. So this would be in, this would be into, and this would be VDD, and this would be ground. Okay? So this is a general rule with CMOS logic. And then basically you're in a situation where the N-type network and the P-type network are never on at the same time. And one end of the P-type network is always connected up to the supply, and one end of the NMOS network is always pulled to ground. There's two places where there are exceptions to this, okay? Two types of circuit structures. One of them is called a pass transistor. Let's say you wanted to build a multiplexer. Okay, multiplexer basically says I'm going to have two inputs and I'm going to have a select, and I'm going to have a single output. And if select is 0, then the output is equal to in1. So if n1 is 0, output is 0. If n1 is 1, output is 1. And if select is 1, the output is equal to in2. That's called a mux, multiplexer. Okay, it's a pretty typical circuit. I'm assuming you guys have kind of seen multiplexers before. Maybe you haven't. I don't know. It's like a logical element that's pretty popular. Okay? So you can make this also from combinator, like from gates. Okay? From like individual and or gates and so on, but it's fewer trans. So you could do, for example, well, you could make this from like maybe 3 gates, okay? Or you might be tempted just to make it from 2 transistors. Okay, how would you do that? Well, if you had, and think about an NMOS, 2 NMOS transistors, and an inverter, and say I put select here. This is select bar, or an inversion of select. And let's say I connected this guy to select. And this was in 1, this is in 2, and I shorted these outputs and called them output. So now, to first order, it looks like if select is 0, so select is 0, this guy's off, this guy's on. So this is an on switch that's connecting in 1 with output, so output is equal to in 1, and if select is equal to 1, then the output is equal to in 2. Okay? So this seems like a really simple, if I just take my word for it now that I could make this from, if I did this with gates, so with gates, I would need, I think I basically need something like, have to think this through, but I think this would be select, this would be in 1, in 2. I'm not sure this really works, but it's something like this. Okay, let's just say. So I would need 3 2 input gates. Each 2 input gate has 4 transistors per gate. So I would have 12 transistors total with this kind of implementation. And with this kind of implementation, I have 4 transistors total. There's 2 transistors in inverter, and this guy and this guy. So it looks like a much more efficient implementation. Okay? Now, there's a problem with this circuit. And anybody guess what the problem is? Now I should have this for, would be a good Starbucks gift. Well, the problem is NMOSFETs. I just said NMOSFETs early on are good at passing zeros. They're not so good at passing ones. Okay? So this makes a good multiplexer when the input, the in1 value or the in2 value is like 0. It won't make such a good multiplexer when the input value is 1. The reason is that it comes from the NMOS transistors, the way it works. So if you guys remember, the current of an NMOS transistor if V gate source is less than the threshold voltage, the current is 0 through an NMOS transistor. If the gate source voltage is greater than the threshold voltage, then you have two cases where you're either in saturation or linear, but I'm not going to go into that, otherwise you're on. And if gate source voltage is less than threshold, you are off. Okay? You guys all with me? Does it remember this? Okay? So what happens when you have a 0 going through this? So let's say I turn this transistor when it's on. This guy is hooked up, the gate is hooked up to VDD. Okay? Or let's call that 1.1 volt for this class. When the input is 0, so N1 is 0 volts, think about what happens. Well, V gate source of this transistor is 1.1 volts minus 0 volts is equal to 1.1 volts, which is greater than or equal to V threshold of this transistor. Let's say the threshold is, call it 400 millivolts. Okay, so that's fine. So basically, this transistor is on, I get 0 volts going across. Okay, now let's look at a case where I'm trying to pass a 1.1 volt, so N1 is 1.1 volt, and I'm trying to pass that through. So what I'd really like, we'd like a 1.1 volt to show up here in this case, right? But look at what happens here. So this guy, N1, when N1 is at 1.1 and VDD is at 1.1, let's say initially this guy was at ground, this side of this guy, right? Initially it was at 0, now I want it to go to N1, which is 1.1 volt. That's what I'd like to do, okay? Initially, you can call this guy your source, right? So V gate source initially. So let me actually, it's easier for me to draw it with respect to time. So I'm going to call this output. With respect to time, V. So I'm going to draw V out. I'm going to draw V, and then I'm going to draw V out, and I'm going to draw V gate source minus VT. Okay, so red is going to be V gate source, and my green, let's make it blue, is going to be V out. Okay, so look at what happened to V out. Initially, V out is at 0 here. Then it's going to start going up, right? It's going to try to go up to 1.1 volt. Let's say this is 1.1 volt. As that's happening, think about the gate source voltage. The gate is at 1.1 volt. The source is at V at the output. So V gate source is shrinking as this is going up. As this is going up, my gate source is shrinking. So initially my V gate source was at 1.1 volts, but it's shrinking as my source value. So the gate is staying the same, my source is coming up, my gate source value is shrinking, and at some point, my V gate source is going to end up being equal to my threshold. So at this point, you are at VGS minus V is equal to V threshold. And at that point, what happens is the transistor turns off. When V gate source goes to V threshold or less, the transistor turns off. So basically, you hold that value on your output as well, which is, so I should have shown these guys crossing, but let me erase this here. So basically, oops, sorry guys. No, wait, sorry. Yeah. So you end up at VDD minus V threshold as your final voltage. So instead of being at 1.1 volt on your output when you try to pass a 1, you ended up at 1.1 volt minus 400 millivolts or whatever your threshold is, or 700 millivolts. So you don't have a good 1 value through an N MOSFET. That's why you can't pass a good 1 or high value through an NMOS transistor. Everybody clear with that? So PMOS has the same issue, but it's reversed. So with a PMOS, you can pass a high value. So with the PMOS, you can pass a good 1.1 volt or logic binary 1, but you have a hard time trying to pass a 0 because the PMOS turns off when you get to 0 volts plus the V threshold. Okay? So this is like a good idea, but it doesn't quite get you there. So people, but it's still very tempting, right? 4 transistors versus 12 transistors is really tempting. So people like sort of up the ante a little bit to get it to work. So you can't get this to work somewhat. Okay, so what they do is instead of doing this, they do something a little bit different. They say, okay, I'm gonna replace each of these guys. So instead of just the NMOS is good at passing a 0 but not a 1, and a PMOS is good at passing a 1 not a 0. Why don't I just put them in parallel? So I put a PMOS in parallel with the NMOS. They're both connected to the input. And the PMOS gets select. And then here I have the same select goes to the NMOS. And select bar goes to the PMOS. So in 1, in 2, and these guys are the outputs. So now I added 2 more transistors. So I end up with 1, 2, so I end up with 1, 2, 3, 4. There's 2 transistors in here, 6 transistors. 6 transistors. And now I can pass both a 1 and a 0 equally well. Because if I'm passing, if in 1 this branch is on, if this branch is on, if in 1 is a 0 value, the NMOS will kick in and pass it through. If in 1 is a high value, logic 1 or 1.1 volts, the PMOS will kick in and pass it through okay. So either way, I'm fine. Okay, so with 6 transistors, I have a multiplexer. Okay, and this combination, so this combination is a pretty popular combination, which is an NMOS and a PMOS in parallel. Okay, it makes a good switch because it passes both a 1 and a 0. Okay, and this is called a transmission gate. This is why when we looked at the latches, if you guys remember the latches, in their inputs or flip-flops, in their inputs, when we wanted to enable their inputs with the clock, we had a transmission gate at the input. So this was a latch. We had, I don't know, we had like phi, which is the same as clock, and phi bar, which is the same as clock bar. And we had the D. So basically, this allowed you to either pass D through when the clock phase was high, or it cut off this guy when the clock phase was low. Okay? So that's why we didn't use a single transistor here. We wanted to get a good 0 and or a good 1 passed. Okay? So this transmission gate does not follow any of the rules of CMOS combinational logic, right? Neither one of these guys is hooked up to ground or VDD. Both ends are hooked up to ins and outs, right? So there's no pull-up network, no pull-down network, and they're both on potentially at the same time. So these don't, the transmission network, transmission gate does not follow those things, but it's used for the specific thing, okay? The second circuit that does not follow the rules is a high impedance buffer, okay? So the second circuit is called a high impedance output. Are you guys all familiar with buses, the concept of a bus for logic? So the idea is you have sort of these lines that are running through, and then let's just draw a 1-bit bus. Usually they're parallel, but let's just draw a 1-bit bus. This bus is running through your computer, and the idea is that different guys can take over the bus, like different circuit elements. Like your PCIe bus is like the backplane of your computers. It's a bus. So any like different chips or different modules or whatever can take over on that bus, and it could be the processors talking to the memory or the processors talking to the hard disk and whatnot, whatever. So different modules will have to be able to take over the bus. Okay? So here you'll also need a different circuit than a normal CMOS logic circuit, because it would be if we had, imagine if you had just inverters available to you, and if you connected them together, they're basically both driving that node simultaneously. They're both driving this guy simultaneously. Because another rule of our CMOS, or the artifact of CMOS combinational logic, is that either the pull-up network is on or the pull-down network is on, but always, always, always one of them is on. At no point are they both off. So if you hook up two of these guys, the outputs of two or more gates, they're just going to fight with each other because the outputs are always on. They're either pulling down or pulling up. There's no neutral stance, okay? So what people do is they've come up with this for this very specific case to drive buses and places where you don't want to fight with other things. What they do is they take an inverter. The top and bottom of this inverter look exactly like a normal inverter. So I'm going to draw them like this. But what they do then is they connect up a PMOS transistor here in series with the PMOS. and connect that to the output, and connect a NMOS in series with the NMOS and connect that to the input. Okay, and then they do select and select bar. So notice here, when select is low, this guy's off. When select is low, select bar is on, so this guy is also off. So when select, so let's call this output. When select is low, output is floating. Or the other way to talk about it is it's in a high impedance state. You'll hear both of those. If you are buying like logic, or you put logic in this high impedance state, means you can use it in a bus, okay? Or if you're doing Verilog simulations, if it's in a high impedance state, the output would look like an X in your Verilog simulation. So everything knows you're in an X. Now you can hook up multiple of these guys together. So if this is my bus, I can connect these guys together and call this select one bar, select two bar. And if select 2 is off, this guy is disconnected from the bus, and select 1 can drive the bus by itself without having to fight this guy, or vice versa. Okay, so this is a high impedance circuit. Again, it breaks the rules of conventional CMOS circuits, because both P and N networks are off at the same time. Okay, but it's needed for this special function, which is to get a high impedance state out. So transmission gates and high impedance outputs. So again, in the latch, we had on the imp, so this is the latch. We had the transmission gate on the input. So this was phi and phi bar. By the way, the symbol for this guy, the symbol is still an inverter, but they put an extra 2 inputs here. So this is, in this case, this would be select and select bar. Okay, because you need to have these extra inputs. But this basically shows whoever's reading the schematic that the logical functionality is still an inverter, but it has this high impedance type of function built in. So basically on the input of the latch, we had this guy. And now on the feedback part of the latch, we use this so this is Q bar, and this is D. Now the question is, what do I put here and here? And why do I have this? Okay, so first look at the case where the latch is holding its previous value, okay? When it's not transparent, when it's holding its value. If you have a 0 here, you have a 1 here from the inverter, and this inverter here will reinforce the 0. So you have this positive feedback loop that's retaining the latch value. As long as this has got power supply going to these 2 inverters, they're both on, they're gonna keep the value, okay? So that's in a storing state, okay? So in that case, I need this guy to be active, okay? So let's say in the storing case, I want when the clock is low, so let's say this is phi. Okay, so phi bar would be the inverse of this. So this is time, and these are sort of the signal values. And then, so what I'd like to do is, while, oops, drew this too far, so. What I want to happen is when phi is on, when phi is on means this input, this guy is on, this switch is working. So D goes to Q bar, it gets inverted and goes to Q bar. Okay, so that's when the latch is transparent. I'd like this off. So I'll give this guy phi to this guy and phi bar to this end. And now, if my D is doing something here, remember this is Q bar because I only have a single inverter in between D and Q bar. So it looks like this. So in the case when the phi is high, whatever happens in the D input, whatever happens here, shows up at the output. It's inverted, but you guys get the idea. It's easy to put an inverter here and get the Q. So if I just put an inverter here, I'll get Q. So let me do that so it's a little less confusing. So Q, so basically that guy will end up there. And then when phi goes low, it basically turns this guy off and turns this guy on, and basically you retain whatever was there before, but you ignore what's on the input. Okay, so that's a latch. And you basically use this transmission gate and this high impedance transistor. Everybody with me? Okay. Okay. So now, let's say the case when we have a flip-flop. So now I'm going to pull up the simulation.